Let's carry on the quantum network session. So we have Mikael Afzelius from University of Geneva, who's going to talk to us on their work towards quantum memories with rare earth spins and crystals. So thanks, man.
Thank you, Henry. And thank you, organizers, for the invitation. First time in Bristol for me as visiting this conference. I like these kind of small conferences, then you actually have the opportunity to meet people. It would be very nice yesterday evening, obviously. Yeah, so I'm going to talk about optical memories, obviously in the goal of doing quantum networks, doing nodes for networks. And I'm going to talk about rare earth crystals. That's the memories we use. And actually I have an example on the picture here. So this is a cryostat, and this we are looking down through the optical window. So here you see one of these crystals, rare earth crystals. Then you have a laser coming in, interacting. Actually, what you're seeing here is this is a yellow laser producing red fluorescence. That's why the crystal looks red. So that's a fluorescence created by the laser as it's doing optical pumping of ions. So this is like a preparation step for our memory. So we use the lasers to interact with the ions, and then we use, you see maybe this coil around it. So the coil is there to interact with the spins. So we used both the optical degrees of freedom and the spin degrees of freedom for doing our storage. So what is novel in this memory that we are developing right now, that we want to talk about today, is that we're using electronic spins. So the best memories so far in this kind of system have been using nuclear spins, and this really gives us some limitation in terms of bandwidth and multiplexing ability. And if you really want to go towards some kind of network like this one that we are thinking about building in terms of the Quantum Internet Alliance, these nodes here that you want to use from quantum repeaters, they need to have larger bandwidth probably than we have now, and most importantly, more multiplexing ability. Because in this kind of systems, if you are trying to distribute entanglement between remote nodes, at some point, if your nodes here are only capable of storing a single mode at a time, then obviously your communication time is limited by the fact that you need to your round trip time is the classical communication. If you can only try to send one mode at a time, you have to wait until something happen. So if you can multiplex that, basically your rate of your repeater will go up linear with the number of modes that you can store. So this is a bit the background. And I think David already mentioned this experiment for us being in Geneva. This is my neighbors. Obviously, we want to help them out also and do long-distance quantum Q distribution. This is obviously the first maybe application you can think of. And this is the state-of-the-art experiment as it is now. So they can do QKD up to 420 kilometers. You see there's like exponential decay here, then gang. You have a drop of rate here, and this is really where you have the limit in terms of noise of the detectors. And still these are good superconducting detectors. This system was made really to break the distance record. So you have good detectors. You want to have a fast system being able to have a high clock rate to be able to do those kind of distances. So this is the state of the art, right? So this is certainly one of our motivations. So this talk will be quite basic, so I hope everyone will be able to follow. So to start with, why do we use spins? I mean, as most of you probably know, the idea is that you want to, for example, take a single photon, couple it to some optical transition. So this is an optical excited state. Use some kind of control field, and you want to transfer that optical excitation into some kind of spin excitation with the goal of having long storage time. Obviously, spins are more protected from the environment, and this way we can get the storage time we need for applications. So I would say most memory schemes are based on some kind of encoding into spin state, whether it's EIT, DSC schemes, Raman, or the schemes we are using based on this atomic frequency concept that I will talk about. So clearly, this is something I think most of you know. Maybe this is a bit unknown outside our community. So what is special with the rare earth ions? When in rare earth ions, we are using a two-step process in going from the optics into the spin system. And what we are able to do is that we can use the fact that we have ions absorbing at different frequencies. So we have this inhomogeneous broadening. So this is absorption as a function of frequency. So every atom has a different excited state energy. Okay, so they are spread out. So that's the inhomogeneous broadening. So this is in our case static. It's given by strain. The strain is a bit different for every ion. So every ion is a bit shifted. On the other hand, every ion in this rare earth crystal, if you cool them down to 3 Kelvin, have very narrow homogeneous line lengths. So every atom can have line lengths down to a few kilohertz, while the total broadening here can be several gigahertz. So you have a lot of absorption channels, and this you can use for storing frequency information. So you can, in principle, come in, this is a kind of cartoon sketch, but in principle you can come in here with a train of photons encoded phase and amplitude information, store at Fourier spectrum in the optical transition. So this is really the basis of the memories that we are using. So so the difference maybe EIT and Raman systems in general are that in some way you're always trying to adiabatically eliminate the excited states. You don't use the excited state. Basically you are going from this to this without spending any time, if you want, in the excited states. You cannot use it as a resource. While we are using it as a resource. Yeah, so I said, so the thing here is what we want to use is that we want to have a large inhomogeneous broadening, but long optical coherence time. Why? Because that gives you the narrow homogeneous broadening, so narrow optical channels. So that's why you have this demand to have also long optical coherence time on top of obviously having a long spin coherence time. So that gives us many optical channels and high multiplexing. But obviously everyone knows that, okay, if you have inhomogeneous system, every atom, if you absorb here, you spend some time in the excited state, you have dephasing. Every atom has a free evolution, which is different. So you need to handle that. And that's where some kind of photon echo scheme, as we call it, comes in. You need to control that inhomogeneous dephasing and undo it in certain ways. And that's the atomic frequency comp scheme that we are using comes in. So it will be just 2 slides, crash course for those who never heard about this. So how do you do it? Imagine now that you are looking at a, let's say, narrow section of this inhomogeneous broadening. So it looks flat, okay, the same sketch. And what we are able to do is we are doing optical pumping frequency results. We can come in and shine lasers at these different frequencies, optically pump away those atoms. Obviously, they will be in some other state, so they are absorbing from other frequencies. But in terms of these frequencies now, they are not absorbing anymore. So we can actually create this kind of comp structure. And what happens is that now if you have an input, which could be a single photon, which has a Fourier spectrum which is wider than the spacing here, so it's covering a lot of these teeth here. What you're having is that your system surely dephases because if you're looking at your decay state here, every atom will have a certain detuning, so you get dephasing. But since this is periodic, you have an automatic rephasing line. It's like any mode laser where you have all the cavity moves in phase. Basically, this is just Fourier response theory, right? So you take the Fourier transformation of that comp, and that gives you a response in time. Right? So the question that often comes, okay, why do you only show one of these ones? Obviously, there are more of them. So let me answer it immediately. Memories are based on 2 things, coherence and what we call collective effects. And collective effects in ensembles is the fact that you have all these atoms interfering collectively to give an emission, strong emission in a certain mode. Okay, so you need a coherence and you need this rephasing, but you also need the strong coupling to the mode. So that basically is given by optical depth, how highly absorbing. So what happens is that if you have a strong coupling, you can emit 100% of the photon here. You can have a very high probability. Obviously, there's a rephasing probability later, but if there's nothing left in memory, nothing will be emitted. So you always have to think about these 2 aspects. Rephasing is an opportunity to emit, and if it emits strongly, you can emit everything at that point. So how do you do a memory of that? Because this is now not on demand, because I send in my photon and it comes out automatically. So what you add is that you want to use the spin degrees of freedom And basically, before this emission time, which is given by 1 over the periodicity of the comb, you are hitting it with a strong pi pulse, bringing down the optical excitation down to the spin state. Okay, you store it in the spin state, and then you reverse the process. You another pi pulse, and you get your photon out. So in this sense, is what other people are doing in EIT and Raman schemes, but we do absorb it in the optical transition. So we do spend some time in the optical transition. So this is typically maybe a few tenths of microsecond that we spend in the optical. So, and now you can, as I said, my cartoon was before that I had these optical channels. You can think about these teeth of the AFCs to be the channels, and the more teeth I have, the more modes I can store. It's really linear dependent on that. So now when you know the scheme, so what do we want? So if we want to have the ideal quantum memory, we want to have a very large inhomogeneous broadening, gigahertz. We want to have long optical coherence time to be able to have many channels. Let's say, I would have hundreds of microseconds. I want to have a long spin coherence time because I'm doing repeaters, so a few hundreds of milliseconds at least, maybe seconds. And this is maybe not obvious. Why do I need high frequency spin transition? Well, obviously, if I want to store a certain bandwidth here, I'm also limited by separation here. I could have gigahertz, bandwidth here, but I have spin states separated by 10 megahertz. They are spectral overlapping. So I also need high energy spin transition. And this is where the new system we are working in is coming in. So maybe I should say that, so the large inhomogeneous broadening actually is something we get mostly all the time. So I would say that's done. So you have to concentrate on the other three ones. And it turns out they are actually kind of depending on the same feature. And that's the magnetic sensitivity of your states. Okay? So if you have nuclear states, so these are nuclear degrees of freedom down here. They are very insensitive to fluctuations in your environment. And the excited state, I only draw like one state, but usually they're also part of some magnetic structure, or some hyperfine structure or something like that. So they're also depending on the same thing. How sensitive are you to some kind of fluctuations in the environment? So this is by no means unique to our system. All solid-state systems kind of suffer from the same. Quantum dot people will know this. NV Center people know this. Usually in your system, you have your active ion, and you have your bath, where you often have nuclear spins. And for example, you have the carbon-13 in diamond, you have silicon-29 in silicon. And this material you will see a lot today. Ytterbium silicate is the best crystal we have in our community because exactly it has the lowest nuclear spin buff. So this is why we all use that. Actually, it has nothing else that is nice. Actually, it has a lot of problems, but this is why we use it. It has the lowest nuclear spin buff. Okay? And that's due to the fact that only yttrium has a nuclear spin to 100%, but it's very weak nuclear spin. It's a Euromagnetic ratio of 0.1, something like that, so it's very weak. Right? So what it does, obviously, is that you have still a fluctuating magnetic field on your atom or your ion, and that wobbles your states. And this is a diffusion process. It's known as the Ornstein-Uhlenbeck process. So there's a correlation time, and there's a maximum spread of it, and that's your bath. So now you can do a very simple order of magnitude calculation. So you have some sensitivity. So you have a linear Zeeman effect, right? So your states are sensitive. And in our crystal, the root mean square fluctuation of this magnetic field here is roughly 5 microtesla. It's not big, Earth magnetic field is what? Is 50 or so? 40, 50? So this is much smaller. Well, this is a variation, and it's not the field on top of the ion absolute value. So you can do a calculation. You take the sensitivity, your gradient, basically, magnetic gradient. You multiply that with that. That gives you broadening. You take the inverse, and you get lifetime, coherence lifetime. So you do that calculation, and you do that for typical electronic spin, where you talk about, this is the Bohr magneton, 14 gigahertz per Tesla, but a nuclear spin is 1,000 times less sensitive. So you expect something like, okay, in this crystal, electronic spin a few microseconds and nuclear spins a few milliseconds. You do some experiments in labs. So this is a typical electronic system. Neodymium has 2 electronic Zeeman states plus minus 1/2. You do a spin echo measurement, you find 1.5 microsecond, and you're not surprised at all. That's what you should find. Right? So that's one reason we don't use nuclear spin, electronic spin up to now. And that's why the memories that use like spin degrees of freedom in our community have only been concentrating on these two, which are only having nuclear degrees of freedom. So this is, you will see my group has used this, the group of the Reed Mountain uses that, and in the States there are also people using it. So this exactly gives quite good optical coherence time at 0 magnetic field. You get millisecond optical coherence time or order of magnitude, and hyperfine coherence time are the same thing, but memory bandwidth are bad because these are really closely spaced nuclear states, and you also have the wavelength here. So I should say one thing here. This is 0 applied magnetic field. So this is what you get by doing nothing because it's nuclear. Now you can do dynamic decoupling and looking for clock states and things like that, and then you get huge coherence time, obviously. So in this system, people have shown 6 hours coherence time by doing different tricks. So that's done in the group from Matthew Sellers in Australia. The question is, do we need 6 hours coherence time to do repeaters? I would probably be happy with a few hundreds of milliseconds if I can get the bandwidth. So this is maybe the trade-off that one needs to do. So just to flash a few results that we have had in the last years. Maybe I'll do quickly. So this is the system, Europium. As you see, you have nuclear quadrupole states separated by a few tens of megahertz, but you do have the nice coherence times. And maybe I'll show this. We've been able to store weak coherence states of a few photons, have quite a reasonable efficiency, or at least non-negligible, I would say. Noise level is down here, so quite good SNR, and lifetime up to millisecond. And this is what we basically take into the Flagship project, because we did show 2 years ago that we are able to execute a DLCC scheme here. So we excite the system, we get the Stokes photon out, we manipulate the spins using radio frequency at 35 megahertz. We read out the excitation, get the anti-Stokes, and we show that these Stokes and anti-Stokes are correlated with a cross-correlation function. So, and this is the delay between the detections. So we have like 1 millisecond. We have memory, it's quantum. We didn't show entanglement yet, but we did violate Cauchy-Schwarz, and it's quantum in this sense. So this works, and this is what one can go to the Flagship because it's technology. I have a memory, it works, and that's what we're doing. But if we want to really solve this bandwidth problem for future, that's where recently we kind of stumbled on a new thing. So let me explain what is different here. So we were investigating with colleagues in Paris, the group of Philippe Goldner, this Ytterbium system. So why? Because it happens to have a kind of unique isotope. It's the only stable, we don't want to radioactive quantum memories. It doesn't go well with the funding agencies, I believe. But so this one is the only one of all stable rare earth that has a nuclear spin of 1/2 coupled to one electronic spin of 1/2. So the lowest non-zero spins of the two. So kind of simple system, no? Actually, that was the only motivation why we did that. And then we stumbled upon something, and this is this. So it has a simple spin system. So you have a hyperfine interaction, and you have some Zeeman term coupling to electronic spin. Okay, so here you have the coupling between the electronic and nuclear one. But let's consider now that you have no bias field, so you only have the hyperfine part, and you diagonalize that. And due to the fact this A tensor is completely anisotropic, 3 different elements, you completely split the states, already field of 0 field, and you have actually 4 energy states. And those are actually the Bell states. So if you look at the projections, these are the 4 Bell states in terms of the up and down projections of the nuclear and electronic spin. So completely hybridized, as we say. Okay? You cannot separate electronic and nuclear properties. Well, Bell states are not polarizable, so the expectation value of the S and I operator with respect to this is strictly 0. So if you do a first order perturbation theory, now you put this weak perturbing field, okay? And you do the first order perturbation theory. What's that? That's basically taking the expectation value of the S operator, but that's 0. So to first order, a perturbing field do not wobble the states anymore. They stay fixed. Okay? And that's what we call a clock state in atomic physics. No? They are not sensitive to magnetic fluctuation. And we went to the lab, or obviously we did the completely opposite. No? We did the measurement and then we figured out why. So my student came and he said that, well, I have some field on and I get 100 microsecond coherence time. In a system we expect to get a few microseconds because it's electronic, no? And then I told him, well, ramp up the field a bit. And what happened, because usually you put more field, you get better coherence time. And the coherence time just went down. Okay? And we were here somewhere when we had no field on at all. Then I told him, well, reverse the field. Maybe we have some bias field. He reversed the field, and then it just went up, no? And we got more and more coherence time. So we had some bias field. And then we did the same on the spins, and by then trying to cancel the bias field, we went up to 1 millisecond. And look at the scale here. You know, it's you're on tens of hundreds of micro Tesla. It's enough to bring it down to scale where you bring out the Zeeman part. So you put a bit of magnetic field and a bias field, and this will break this nice feature. Okay, so you really have to be as close as 0 as possible, and this holds them. I guess this is one of the reasons was never observed in our system. No one looked for it, and you really have to be a bit lucky not to have too much bias field. It's easy to have 100 microtesla in your lab, and you wouldn't see this. So I guess this is one of the reasons. I think I skipped this one. We had another magic point that we also could use. And now if you, at 0 field, if you compare what we have, so we achieved 200 microsecond optical coherence time at 0 field, 4 millisecond at the hyperfine levels, but we have state separations now that amounts to hundreds of megahertz and gigahertz. So this is where we see a bit of potential now, trying to do some more high band memory and not sacrifice too much the coherence time. So how many minutes do I have left? Yeah. Okay. So that's where we are now, and so we published that, and we have a student to build up a kind of proof of principles experiment, basically to show research and also funding agency that this is viable. We can do some memories in it. So it's very preliminary. So we focus on this Lambda system here. This is an optical absorption spectrum. We are coupling these states here. We're talking about 650 megahertz hyperfine transition, and these are the optical transitions over here. We can do Rabi flops on the microwaves, on the optics. And here you really see actually the electronic feature. This is funny. So while they are insensitive to DC fields, the transition moments stay electronic. And if you know optics, this should not surprise you. Know? In optics, if you have an electric dipole transition, your diagonal elements are strictly 0. You can drive them, no? And this is what's happening here. So you're making the diagonal elements of the tensor, the dipole tensor, go to 0. But actually, if you look at the driving, actually it goes like electronic spin. So with very little power, we are sending milliwatts of power, and we can drive it at megahertz. In the nuclear system, we have a big amplifier of 100 watts that we send to do 50 kilohertz Rabi frequency. So here you really see that you get like the good of the two worlds, a high driving frequency and low sensitivity. Okay, so the experiments we build up. So here is an example. Don't be scared, but this is what happens when you do rare earth. You have these like absorptions. You shine laser in it, and you get this kind of absorption spectra here. So don't get confused. Only 4 frequencies are relevant here. We are having a lambda system here, right? And we are using these to just optically pump system. For example, here we start by polarizing everything into this state. You see the high absorption here, we try to empty this, so you see kind of dip here, and then you see dips over here and here. That's where we empty this one. The other things are not relevant. And it looked like here someone can say, but your bandwidth will be limited here. Actually, it's not true. All these features here, I mean, I can pump those ions that absorb there into other states, and I can actually make an atomic frequency come over hundreds of megahertz. We already tested that, so that's fine. So this is an example over a 20 megahertz atomic frequency come that we created in this very region here. So then you send in some input, and you see your AFC echo coming out. Quite decent efficiencies for first try. So this is as function of storage time. Here there are no control fields, so we just make the AFC, send in the pulse, and we got the echo out. So we didn't apply the control field to convert it into spin excitation. So this is just this it's not the on-demand memory, but these are the time scales that we never ever achieved in any electronic system. So these are time scales, because it is related to the optical coherence time here, we only ever achieved on nuclear systems. So already this was a kind of a nice confirmation that this is really viable. And we did obviously try to put the control fields, make a full memory scheme. So we have an input, we have the control field, the optical one. We manipulate the hyperfine state with 654 megahertz radio frequency or microwave pulses to do spin echoes, and then we read it out. And we do see a memory. We have something like 3% efficiency right now, and we do have lifetimes of 1 millisecond. So very similar to what we had in the nuclear system before. So this is where we stand right now. I should emphasize that everything here is done with photodiodes and no single photon counting. We have not shown yet that this is possible to do at that level. These experiments have been done the last 6 months or something like that. So let me wrap up then. I hope I convinced you that if you really want to do repeaters, we need memories that can combine high bandwidth, large multiplex, and lovely memories. And while every of these aspects has been shown in different experiments using Raman memories, using cold atoms and so on, the real challenge is to do the three simultaneously in one system. And I think this is still a very open question. And I think rare earth crystals have are good candidates for this. It could provide that. But it will require to use electronic spin, so some kind of trick with electronic spin, some kind of clock states on them. And I think the Ytterbium is good here, and it looks good in the lab. But obviously, to really go further, there are many things we need to do. And the three key areas I would say we need to work on is that, well, while we have decent now coherence time, actually our theory predicts even longer. Maybe you noticed there was a red curve here, and actually it goes up quite much higher. We would like to understand why there is this. Did we not cancel the bias field properly, or is there some other mechanism we haven't accounted for? So this is one of the most important things I think we need to address. And then we'll try to use dynamic decoupling and other techniques to even prolong it further. So the goal is to try to do 100 millisecond. I'm not sure it's possible, but that's the goal. We want to boost the Rabi frequency in the optical transition, because what does it help you to have large splittings here, large bandwidth, if you cannot transfer that using this pi pulse? It has to have a Rabi frequency which is considerably larger than anything we ever produced before. And rare earth are kind of bad here because they have low dipole moments. So the way to go is that it's been shown by the group of Roberto Salam and Ytterbium that one can, on our favorite material, now engrave laser-written waveguides on top of this one. And using the field confinement, they already show that you can greatly enhance the Rabi frequency using the same optical power. But there are a lot of, this is really new, and there's a lot of open questions about if you, for example, by doing this waveguide, degrade the material properties, for example. Do you have less coherence time? So this is an open question. And we got a bit inspired by what people have done in envy centers. So this is the kind of microwave 3D lumped element resonators that the group Johannes Meyer is using in IIT in Austria. And what it does is that it creates a very homogeneous microwave driving field over a large volume. You have to remember that our crystals are like 1 centimeter long. It's very challenging to create a very homogeneous driving field to perform a Rabi flop over the whole volume. And this system is providing that. So inside here, you have between these elements here, you have an oscillating field along the direction here, which is very homogeneous. And on top of that, you can make holes in the box and put a laser through. So we actually, this is from my lab, and we are investigating now to couple light and microwaves through such a thing to achieve both, and ideally with a waveguide on top of that wave crystal. So let me just acknowledge the people who have done all this work. So the main person behind is Alexa Tiernov, a postdoc, who's now going to Peter Lodal's group working on other things, and Antonio Orto, who did a lot of spectroscopy work in the beginning, and Maurice Bussinger, who has now been setting up this memory experiment, and myself, of course. So thank you for your attention.
Thank you very much for the fascinating talk. That was really great. We have time for one quick question. Anyone? Elizabeth here.
So what do you think is limiting the coherence time at low field? Is it the temperature or something else?
Right now we believe it's actually Ytterbium themselves as well. So I only talk about the nuclear spin buffer yttrium. I mean, we didn't think that in the beginning because we only have 10 ppm of Ytterbium 171, so it's extremely low. But colleagues in Paris, Philippe Gaudin and his group, have used some kind of broadband optical pumping to try to basically get to all the spinors in a whole inhomogeneous broadening and put them in one of the hyperfine states. So it's kind of tricky because you have to pump over gigahertz. But by doing that, they are seemingly reducing the flip-flop rate of the Ytterbium themselves. And they actually went from 200 microsecond optical coherence times to 800 microseconds. So that's, and surely this is not the limit. So that's the first part, probably. And by doing that, we hope also to be able to perform dynamic decoupling of the spin states. Because we were trying, we were not successful, and we believe this to be one of the things. And then maybe bias field we didn't really control. So, but it's a bit open.
Great. Let's thank Mikael again.
Thank you.